Hey everybody, I hope you're doing well. We're going to start this week off with some review of polynomial functions. So this first thing that you see here is a polynomial if we're talking about technical form, okay? All those coefficients are the a values, a sub n minus 1, etc., all the way down to a sub 0, subscript 0, that's how we say that. So a sub n would be the leading coefficient because n is the highest exponent, because then the next one is n minus 1, n minus 2. So for example, if n was 10, this would be the leading coefficient on the 10th term. This would be x to the 10th. Then this would be the leading the coefficient for the 9th term, x to the 9th, x to the 8th, all the way down to a sub 0, which means it is the constant, the last term. Okay, that's standard form. Okay. A sub n, like we said, is the leading coefficient. So quick little overview from the table. Each of these are classified by the type of degree. Degree here is 0, so it's a constant, leading coefficient 4. Degree here is a 1, so it's linear, leading coefficient of -5. Degree here is 2, so it's quadratic, leading coefficient of 12. Degree here is 3, so it's cubic, leading coefficient of -1. Next one is quartic because degree 4, leading coefficient of -3. Next one is quintic because it's degree 5, leading coefficient of 9, and these are all in standard form. Okay, polynomial parent functions. We actually took notes on these. It's a light pink sheet, so you should have some of these down on that paper if you have it with you. But parent function of a constant is y equals c. I just called it c because it could be any number. So for example, y equals 2. Okay. Next one, linear parent function is just y equals x. Simple, remember parent function means just the most simple, nothing multiplied, divided, added, subtracted to it from it. Okay, quadratic is just y equals x squared. Cubic is y equals x cubed. Quartic is y equals x to the 4th. Should be more slender than a quadratic, can look similar to a quadratic. Quintic is y equals x to the 5th, again more slender in comparison to the cubic function. What we really want to get into now, that's just kind of the stuff that we've seen before, is end behavior patterns. And so I hope you looked at the 3.9 stuff in the Desmos activity and kind of got an idea of end behavior patterns that you are noticing. So two key things that we want to look for are, what is the degree? Is it odd or even? Is the degree odd or even? So that highest exponent, is it an odd number or an even number? And then what's the leading coefficient? Okay, so if we can kind of know that, then we don't have to use a graphing calculator. You can, and you can use Desmos, but for this, we're just going to kind of go through and analyze it according to the type of degree that it has, and then the leading coefficient. So for this first one, degree is 4, so that's an even degree, okay, which means it should behave like the simplest version I can think of is a quadratic is an even degree function. So we know that parabolas either open up or down, okay. Since it's a positive leading coefficient, I know that this should have the same end behavior and it should be opening up, okay. So I should have positive, positive, awesome. The second one, it is a quadratic, but it's negative, so we know it should be opening down, which means both y values should be going towards negative infinity. Okay, and we have done end behavior before. Remember, this just means as x approaches positive infinity, aka if x goes to the right, y is going up, right? That's how we say that in non-mathy terms. So this is saying as x goes to positive infinity, y also goes to positive infinity. This one says as x approaches negative infinity, aka goes to the left, y approaches positive infinity as well. Okay, just as a little refresher. Next ones, we're working with cubic functions for both 3 and 4, okay? So that means they are odd degree polynomials, okay? The degree is a 3, it's odd. So opposite end behavior. The simplest odd function I always think of is a linear function, x to the 1st. Okay, so positive leading coefficient should look like a positive slope. Okay, negative leading coefficient overall would look like negative slope. Okay, but opposite end behaviors. So here, this is what we've got. Okay, so as x goes to the right, y should be going up. As x goes to the left, y should be going down for number 3. For number 4, as x goes to the right, y should be going down. As x goes to the left, y should be going up. And again, if you're having trouble seeing this and understanding this pattern, because maybe you still have questions about it, plug these into your calculator. Go back, go see the problem, pause the video, go graph it in Desmos, or go graph it in the graphing calculator. Remember the graphing calculator link? There's a link I posted on Google Classroom really early on, and TI is giving free access to their graphing calculators online, so you just got to go in and download it. It's awesome. All right, maybe these ones, go ahead and pause the video. So number 5, you've got a quadratic with a negative leading coefficient. Number 6, you've got a cubic with a positive leading coefficient. So maybe pause the video and take a look at those. Okay. I don't know if this is, yeah, okay, it is going, hopefully. So if you checked these out, this should be opening down. This should be, so I would say it's going to look something like this. This one would look something like this. Okay, so this should have, for number 5, should have the same end behavior, negative. Number 6 should have opposite end behavior. As we go to the left, it goes down. As we go to the right, it goes up. Okay, so the next little part is just drawing sketches to help us remember. So if you need to, draw a sketch of something like a parabola. So a positive leading coefficient even degree would be like a parabola opening up. Okay? Negative leading coefficient would be like a parabola opening down. So one way you can talk about end behavior in kind of a shortcut is to do like a coordinate point. As we go left, it's going up, comma, as we go right, it's going up. That's one way to write it. So this is kind of like number 1 that we saw up above. Okay, so even degree, positive leading coefficient. Okay, number 2 is like this one, negative leading coefficient, but even degree, right? So it looks like a parabola going down. So as we go left, comma, as we go right, it's going down both directions. Okay, odd degree, this is like 3 and 4. Okay, positive leading coefficient, overall, it's going to look like this, right? There's going to be some curves and stuff in between, but it's going to look like a linear function with positive slope. This one's going to overall look like negative slope. Again, there's going to be some twists and turns in there, but simplest way to think about it, think about what you know. Quadratics, think about linear, and what happens if they have a positive or a negative leading coefficient, and that's going to correspond with the family of even degree polynomials, x squared, x to the 4th, x to the 10th, x to the 100th, or in this case, odd degrees are going to look like linear, right? X cubed, x to the 5th, etc. All right, so this last little part is going to give you some functions. They're going to ask you if there is even degree or odd degree, and if it's a positive or negative leading coefficient. So for number 7, the function that you're given opens down in both directions. There's some curves in between. So I would say since it's the same end behavior, it'd be even, okay? And then leading coefficient, since it's opening down, should be negative. Now, based off of what I know, there's 1, 2, 3 turning points, so I would guess that this is a quadratic. Or not, I'm sorry, not a quadratic, a quartic graph. Okay, number 8, the graph you're given is this. And again, I drew on it because it's opposite end behavior, so we want to think about what it would look like if it was a linear function. Okay, so I'm going to guess that this is odd degree polynomial, because it's got opposite end behavior. And then if we draw kind of like the slope from the endpoint to the endpoint, it looks like it's going up overall. So we would say it's got a positive leading coefficient. Okay, so with this one, I would guess that this is a cubic function because it's got 2 different turning points. That's what we're going to start talking about now is turning points. Okay, turning points are places where the graph switches direction. So on this graph right here, the turning points are going to be in red. There's a turning point here, and there's a turning point here. Okay, and so This we would call a relative maximum because it's higher than any of the nearby points.
And our card does.
Okay, and then this one down here would be a relative minimum because it is lower than any other points in the area. Okay, so the maximum and minimum values overall are called extrema. Okay, and then the next thing we want to talk about is turning points kind of set up where the function's increasing and decreasing. So increasing means as we go right or left to right on the graph, just like how you read. If it's going up, we call it increasing. So the two parts of increasing on this graph I made green, okay? Because from left to right, the graph is going up. The part where the graph is going down from left to right, we would call that decreasing. So I'm going to talk to you in just a minute about how we set that up. Okay, so the next part, like I said, we're going to find the turning points of each function, and we're going to use the graphing calculator to do it. You could also use Desmos, that would be fine, but we're going to go through the steps of how to graph on the graphing calculator. Okay, so we're going to go to y equals, and we are going to plug in that function x cubed minus 6x squared plus 7x plus 2. Okay, so when you go to the calculator, we're going to go to y equals first. You want to make sure it's cleared out. So if yours doesn't look like mine where it's not cleared, you want to make sure that you have cleared out the calculator. So you go clear. You want to make sure all those plots are de-highlighted. Okay, so we're going to plug in x raised to the third. Okay, arrow out, minus 6x squared plus 7x plus 2. Okay, so everything's all set up, and then I want to go zoom option 6, zoom standard, unless we need to change it if we can't see the whole graph, but it looks like we can see the whole graph here. Okay? Okay, so the next step after we've got it graphed is we are supposed to then use the calculate menu to find the minimum and maximum values. So that's second trace. Okay, and so second trace, let's find the maximum value first because it looks like that's what we're closer to. So left bound just means we want to point on the left. So we are on the left of the maximum. We hit enter. Then I arrow right to pick a point to the right of the maximum. I hit enter, and then we could just hit enter again for a guess, and it's going to give us our maximum. So you can round to 2 or 3 after the decimal. For my sake, I'm just going to round out to 2. So I would say that the relative maximum occurs at 0.71, 4.30. Okay, we're going to go through the same process then, but find the relative minimum. And it's called the relative maximum and minimum because it can't be the overall, because we know the function is still going down on the left, and on the right it's going up. Okay. On Desmos, if you use Desmos, it's really awesome because you can just click on the point and you can find exactly what it is. Okay, now I just selected minimum. I went second trace and I selected option 3, which is the minimum. So I want to find a point to the left of the minimum, and I'm going to hit enter. Then I find a point to the right and I hit enter. And then I'm going to hit enter again when it asks me for a guess. Okay, and I'm going to call this point 3.29, negative 4.30. Okay, so we're going to head back to the other screen and get those in. And then we want to look at the increasing and decreasing intervals. Okay, so here's the relative max, here's the relative min. Okay, when we're looking at the graph, it looks like kind of a sketch of the one that we had on our notes. Right? It's kind of a cubic function that looks like that. So my increasing goes from negative infinity to my point that is the maximum. And then the other point of increase would be from the minimum to positive infinity. And when we are looking at these areas of increasing and decreasing, we just focus on the domain. So I would say my area of increasing would go from negative infinity to 0.71. And then from 3.29, which is the x-coordinate, to infinity. Okay, then the decreasing happens in between. I will fill out the rest of these notes and post them on Google Classroom for you to check. So go through these and double check